Okay, so now we're going to talk about the second chapter, which is crystal structure. So in crystal structure, we started off with the difference between crystalline and amorphous solid. So it's basically an ordered solid is crystalline, where you can take this single unit cell and you can actually repeat it in 3 dimensions. So that's what we wanted to do it. But amorphous solids are something that you cannot do that because they don't have this ordered structure. So some of the amorphous solids examples are wax, your glass, like these are like amorphous solids. So most of the metals that we're going to deal with, like steel, aluminum, copper, they're all ordered solids. So to start off with, like we have this 7 crystal systems. Seven crystal systems. So I'm not going to list everything, so it's on the book, so you can go take a look at it. It's cubic, tetragonal, orthogonal, trigonal, hexagonal, triclinic, and monoclinic. So the most important thing that we're going to do here, the 2 things is basically your cubic structure and then your hexagonally closed packed structure. So each of these crystal units can have 7 unit cells. So you're going to have 28 unit cells. But obviously we're going to have only, so this 28 is going to transport into 14 unit cells. And we showed how one of them transforms. So for instance, so everything is going to have a simple structure, a body-centered structure, a face-centered structure, and a base-centered structure. So one of the examples that we did in the class is like if you take a base-centered cubic structure. So I'm going to draw another structure in here, so it's something like that. So if you think this is the base centered, so these are the bases. So if you think this is the base of this structure, so this is the base of another structure that's sitting on the top. So what happens is you can connect these dots like this. So this is basically your base centered cubic. But we only take this as simple tetragonal, like the one that I showed here. The reasons for that we didn't go into it because of symmetry and all those things. So simple tetragonal in this section, what it happens is it's A equal to B but not equal to C. So you have this square sitting on a length side here. So this is the simple tetragonal. So like this, if you keep knocking them out, all of this 28 unit cell is going to transform into this 14 unit cells. So out of this 14 unit cells, we're going to only look into 4 of them. So the first one is simple cubic, SC. Then you're going to have body centered cubic, which is BCC, and then face centered, which is FCC, and then hexagonally closed packed system, which is HCP. I'm not going to write the whole thing in there, but you know what it is. So now all of these things, what we can try and understand is like you can know how many number of atoms packed in each of those. So you can see in simple cubic you can have 1 atom, here you can have 2 atoms, here you can have 4 atoms. And I showed this using this expression where the corner atoms divided by 8, the interior atoms divided by 1, and then the face atoms divided by 2. So you can do all of these things, and you can calculate the number of atoms, the coordination number. It's a little different for HCP, where the corner atoms is basically divided by 12 rather than 8, because it has 6 times 2, there's 12 corners in there. Okay, so then we have to calculate APF, which is nothing but atomic packing factor. Okay, you can actually calculate the atomic packing factor is basically how well the atoms pack inside the unit cell. So you can actually calculate it by knowing the number of atoms in that unit cell. So now you know if it's a simple cubic, that's 1 atom, BCC is 2, FCC is 4. And then you multiply it by the volume of atom, which is nothing but atoms are hot-sphere in this case, so it's 4 by 3 pi r cubed, and then you divide it by volume of the unit cell. So unit cell for the cubic structure, it's nothing but a cube, but you can also do it for HCP, which we did it in the class. So if you go and take a look at that, that's basically you separate it into like 6 triangles on the bottom, and then you basically get it into 3a square c sine 60. Then you should know what the A by C ratio is to get to that. So when you do it this way, the APF, you can actually calculate it for all of these structures. So simple cubic is about 52, so only 50% is completely packed. BCC improves a little bit to 68%. For FCC and HCP, which are the most closely packed of all of the 14 unit cells that we talked about, it's about 75%, 0.74 and 0.74. That's right. Okay, 0.74 and 0.74. Then we can also calculate the density of any given element by using this formula, Na divided by Vc and Na. So you know this is going to be the number of atoms. And this is going to be the atomic weight. This is the volume of unit cell. This is Avogadro number. So you should be able to get the Avogadro number from the constant table. Atomic weight, you should be able to get it from the data table, number of atoms and volume of units. So you should be able to calculate it based on what crystal structure it is. So if I'm asking to find the density of aluminum, you have to find it using this formula, and just don't get it from the table and just write it down. You're not going to get any points for that. Okay, so each of these elements can have different crystal structures. They exhibit different crystal structures. We talked about that as polymorphism. So the diamond, graphite, iron, and then tin. There's these different examples. So we also call this as like allotropy. So it doesn't matter what you call them. It's either more polymorphism or allotropy. Then we talked about stacking sequence. So stacking sequence, how you can stack them. So if you stack it AB, AB, then we call that as HCP. And then if you do ABC, ABC, then it is basically FCC. So if I'm telling you that aluminum stacks itself ABC, 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 then you should know it's an FCC cubic structure. And then if I say zinc stack itself as AB and AB, then you should know it's an HCP material. Okay. So we talked about directions. So take a look at directions. There's a whole lot of way how we can do it. So we did these directions and planes only for cubic structures. So again, now we removed HCP from directions and planes. We only did it for cubic. So you understand what a family is, how to do the directions first, how to do the family, linear density. So plane, there's basically 3 planes that are important, and then also try to understand what a planar density is. So this is basically the face of the cube, and this is the diagonal, which is like going to look like a rectangle, and this is connecting the corners, which is going to look like this. So now you should know, if it's a simple cubic, the atoms are going to go sit like this. Okay. If it's the same thing as a BCC, then you're going to have no atoms here, but here the atoms is going to sit right there. And then here, the atoms not going to sit in there because this plane is tilted a little bit to the angle, so it's not going to cut through the center of the atom. So if I'm going to ask for linear density and planar density, if you know what is in terms of unit cell length or atomic radius, then you should be able to know what is the relationship between this. So the relationship between A and R for simple cubic, BCC and FCC. Try and understand that and how to get to that. Then finally we finish this chapter with XRD. So where it follows Bragg's law. So I'm not going to go into detail about what it is. You can go take a look at the lecture notes. But one of the expressions that we're going to do, the Bragg's law, is n lambda 2d sine theta. This is the order of reflection. It's first order in our case, so which means it's always going to be 1. N equal to 1 always. And this is the wavelength of X-ray, which we call as lambda. It's always given in angstrom, which is nothing but 10 power minus 10 meters. So you have to expand it to get this. D is nothing but interplanar distance. Oops, what am I doing? Interplanar distance. Let me find that space for you now. Okay, interplanar distance, and this theta, if it's given as diffraction angle is always 2 theta. So this is just theta, so you have to divide this by 2 to plug it in there. Okay, and then for cubic structures, the interplanar spacing and the lattice parameter is always given by this expression. Okay, so if I say this is 1, 1, 1 plane, so this is nothing but A divided by 1 square plus 1 square, which is A divided by root 3. If this is 0, 1, 1 plane, then this is nothing but D equals to A divided by root 2. So on and so forth. So this is D and this is A. So once you know what A is, you can calculate R, which is the atomic radius, for BCC, SE, and FCC. If you know what it is, then you should be able to calculate that relationship. So this is atomic radius. When we talked about ionic bonding, it's basically ionic radius. Ionic radius and atomic radius. Try and understand the difference between them. You can get both of these from the table, and yeah, so use it appropriately. Ionic radius and atomic radius, difference between them. Alright, I'll see you in the next video, which is chapter